Yeah, so we talked about Lempel ZIF encoding in the last class, and today I want to talk about Skiplist. And before I talk about Skiplist, I think we didn't even talk about Doubly linked lists and Multilist, and we will see some applications where these data structures can be used, and then we'll go on to the skip list. So let's look at, we already saw, I think we already saw the circularly linked list in the class, in the tutorial. List in the tutorial, and we saw how a queue can be nicely implemented. Even if you have only one pointer. Okay, something like this, and you make that pointer P point to the rear. And now, what's the advantage of a doubly linked list? Let's see this. So if I have something like this, let's say I have something like this, A1, A2, A3, A4, and A5. So what happens is, I have something which is goes forward, a forward going pointer, and also a reverse going pointer. This to this, and this to this. So the good part is that you can traverse from either end. Traverse from A1 to A5 or A5 to A1. What's the advantage of this? Is primarily in deletion. Remember when I used a linked list for representing a queue or a stack, I used a dummy node. Because why did I do that? Because the deletion was easy when I kept it up. Deletion became easy. Here on the other hand, I don't need that at all because I have access, because if I want to delete A3, let us say, then I need access to this pointer to A2 is required. Okay, in a singly linked list. In a doubly linked list, that can be avoided. Now, nothing prevents us from making this circularly doubly linked list, and this will have its own advantages and so on. So what is interesting is using an array and linked list, I can linked list, we can make a number of different data structures. Okay. Remember we saw the tree, right? Representation of the tree using the array where we had parent pointers and so on. Now, but of course, the extra work you have to do, work of adjusting pointers, double the work actually, for a doubly linked list. but it may save some operations. We can also look at what are called multi-lists, and typical example is, suppose we have IT has 10,000 students, and let's say there are 1,000 courses. You know what seat allocation actually does. So let's say I have the course of C1. There are two kinds of operations that we want. Let's say we need 2 reports, and this is basically registration for every class, and the list of courses for every student. And also it should make sure, of course, it doesn't take care of the prerequisite seat allocation, where we had lots of problems in this particular course. So I would have something like this: C1, C2, C3, C4. So I would have a list like this. And let's say I have the list of students S1, S2, S3, S4, S5, and so on. Then let us say S1 was registered in C1, like this, and maybe he was she was registered C3, so connect like this, and maybe he or she did not register for any more courses. So this will be C1's information, S1's information. Similarly, let's say I have the S2 is not registered, S3 is registered for C1, and S4 is also registered for C1, and S5 is also registered for C1. Then if I want the list of students who are registered for this course, I can go down this. If I want the list of students who are registered, list of courses a student is registered, I can go down this list. So both these things are possible. Again, you have something like this, like this. You can start from any course, go to any course. That's the advantage of a circularly linked list. The third application is of multi-lists. These are also called multi-lists. Is a representation of sparse matrices. For example, let's say you have a matrix, large matrix, let's say 100 by 100, and most elements are 0. Then even here, you can use a linked list representation, and so you could have a header which corresponds to the number of rows. So basically what do we need? We need the size of the matrix. We need size of matrix. And what do we need? We also need the location of every element in the matrix. For example, suppose I have a 6 by 6 like this. Yes. Yes. Then what do I have here? Let's say this is the 0th row, first, second, and third. Then all that I need is 0th row, 0th column. So 0th row, first column, I have 1. And I have first row, third column, I have 2, and so on. Okay. Similarly, I have second row, first column, 0th column, I have 1, and the second row, fourth column, I have 4, and third row, second column, suppose I have numbers like 0, 1, 2, 3, 6, 5, 4 lists, so 5, 6. So I have third row, second column, 3, and so on. So notice that we need only 5 pieces of information. Formation. And why to waste 6 into 4, 24. This can be avoided by using multilist. Different ways of representing it. You could use a header for every row. And row 0, row 1, row 2, and so on. Row 3. And give the location of the elements. And first one would be, you have 0, 1 stored here, 0, 1, 1. And 1, 3, 2, and so on, 2, 4, 4, and 3, 2, 3. Gives you the row, the column, and so on. You can also make it like this. I'll tell you why we do this. Now what I can do is I can also connect it column wise. For example, suppose I had an element in the first column, then I could connect even this way, add additional pointers to point to elements in that particular. So you can just like a regular 3D array. You can traverse across columns. To doing some operations, for example, columns are used. Suppose you want to find the transpose of matrix, you can do both of these things. So this is another way of using multilist. So now what I'm going to talk about is finally this idea of what a skip list is. Skip list is kind of somewhat related to hashing and also related to sorting and basic idea of a skip list. Let's see where it comes from. A sorted array with n elements can be searched in order log n time. Okay. Whereas even if you have a sorted chain list, searching takes order n. The idea is to avoid this. What we do is we place additional pointers and what these pointers do is help skip over several elements or several nodes. And during search. And this is what gives you the saving in time. Basically, unlike a linked list, need not search every node from left to right. Okay. Basically, what we're talking about is if I take a sorted chain list and augment this list with additional forward pointers called skip list. So you improve the performance of search and this can also result in improvement of performance on insertion and dimension. Let's see how. The simplest idea is, let's say we saw if it is a sorted list with an element, we need ON comparisons. We want to reduce the number of comparisons. Two, let's say I can make it n by 2 plus 1 by keeping a pointer to the middle element. Let's see this example. What do I mean by that? So we normally have one header and one tail node. Then let's say this is 20, 4, 30, 40, 60, 75. And let's say this is what I have, 80. And then I also have a tail. Okay. Then what we do is, when I want to keep something to the middle, I augment this, add another pointer, something like this. Okay. Then this original list is called level 0. Then now if I augment it with a pointer to the middle level, now I compare with middle. For example, suppose I'm looking for 65. Suppose we want to see a 65 in the list. So what do? We take this pointer up to the n by 2 level and check if there is an, when compared with the 40, it's greater than 6. So clearly it's greater than 40. It's greater than 40. Okay, so I only need to compare with these values. So what we can do is we can generate, we can, in general, so there are, so obviously this is one, n by 2 is one level. I can do level 2, level 3, and so on. Is one such. Okay. So in general, the idea is the following. So you have pointers at various levels. Pointers at various levels. Okay. What is the level 0 chain? All elements are in the chain. Level 1, every alternate element. And level 2, every fourth element is in the chain. Is in the chain. Okay. So level I in general includes every 2 to the I element in the chain. So this is precisely the idea. So for example, in this thing, I could also have something like this. One more pointer like this, which goes like this, and just like this, and comes with it. Okay, I could have something like this. One more, that will be a, this will be a level, sorry, this will be a level 0, there will be a level 1 and a level 2. Only 8 nodes. Okay. So this is very nice. So searching, what do? We start with highest level. Suppose I'm start looking for 77. I check with this level. I check with this level. Then I realize it has to be in this part of the chain. Then I check with the second level chain, 75 is greater than this, and finally I look into level 0. So you notice that you only need 3 comparisons, 3 or 4 comparisons, log n comparisons. But it's all very well. But what about insertions and deletions? It's important to point out that when you look at an array also and look at sorting, we only talked about searching sorted array. We only talked about searching for an element in there. We never talked about inserting. Inserting can be maintenance of the list of the regular structure requires order n. The way of cleaning this beyond the scope of this particular course, and I'll just tell you what this means and close it. So an attempt is made to approximate structure. In fact, Skiplist is a very popular structure for for randomized algorithms, and that I'm not going to talk about. A lot of work that's going on in this particular area, and I'm no expert. So the way we look at it is, when you look at a particular level, I take a level I, then there are n by 2 to the power of I elements at that level. So when an element insertion is made the level of the element, the level of the element is I with probability 1 over 2i. Okay. Actually, one can use any probability p. And we assign we can assign the node to level I with probability e to the power I. Okay. And in the example, for example, we are saying p is equal to 0.5. Then we put alternate nodes, fourth element and so on. So for any p, the number of chain levels is log of 1 over p n floor plus 1. Okay. The skip structure essentially tells us that the level I chain comprises of every 1 by pth node of level I minus 1. This is a crucial property that we use. Now suppose we want to insert 77 in this list. Okay. So when you look at it, what is the last level pointer that we are associated with? Okay. Okay. What happens? Let's say we want to insert 77. So what do you do? We come across the pointer at 40 and okay. So first of all, pointers have to be broken. be broken. Okay, let's think of regular insertion. Okay. To make the insertion, we need to assign a level to the new element. This is the fundamental problem, to see which level to the new element. Because as soon as the pointers break, now it's going to be a problem, right? That structure which we talked about, the p equal to pointer. If you want, it's not going to be there. First of all, new element is at level I, then only pointers from level I to 0 are cut. Others are kept as it is. So in this example, what will we do here? We will put one new element over here, and then we'll insert 77 here. Let's say we adjust the pointers. Then what we have to do is we have to assign the 77 which is inserted here a particular level. That's where the problem is. Okay. Then what we do is, so that's one thing that we have to worry about. Deletion, there's a problem. We have to adjust pointers. So that was insertion. Deletion, we have no control. Over the pointers. Okay. So let's see how we can assign this level to the particular node. And so the problem is assignment of levels. To a newly inserted node. Okay. So we observe that in the skip structure, a fraction of P of elements on level I minus 1 chain are also in I. Okay. Therefore, the probability that an element at level I minus 1 is in I is P. So this is a very simple way. So how do we decide whether a given number should be done on a generate a random number between 0 and random. Randmax is the largest number that can be generated. Random number generators are available in any machine. And what we do is, then we, let's say that we define what is called cutoffs, which is equal to T star randoms. If the generated random number, let me call it rand, is less than cutoff, then we less than or equal to cutoff. Then we Then the new element. Remember, all elements are there in level 0 tree. E is in level 1. Then you take again, repeat the same thing as you. So then, for example, so let's say now this is some level I. E is at level 1. Then for level 2, again you generate another random number. Whether it should be, whether the given number should be in at level 2. You again generate another random. Generate one more random number. Because a fraction of these, one more random number, and keep repeating this. But of course, you can go keep, but so you decide upon the maximum number of levels. Proof of n to the base 1 over k plus minus 1. So, this is the total number of pointers that you have. Even if, but of course, there can still be problems, even if we set upper limits. Because of the random number, it's possible that a number will be there in the region. Is a finite problem. But the good part is because these are like, one way of looking at it is, and this is beyond the scope of this course. You learn about this in your next level course or randomized algorithms. The important point is that the Skiplist enables you to provide fast pointers using which search can be done fast. Okay. Once you've searched for the element, it's like insertion sorting. You have to insert a new element in the appropriate place and then assign a level. So you randomize the number of levels. So this comes to the close of what I wanted to talk about. So let me stop here. This is about Skiplist. And in the next class, we will. Oops.